Hello, Matthews Gatos here. Welcome to part 2 of related rates. So in this video, we're going to cover triangle type problems. So here are my tips for these ones here. For these ones here, you definitely want to draw a diagram just to help you visualize the problem and assign any variables to all given and needed quantities. Now, because these are dealing with triangles, I want you to pick an equation that represents this situation. So you might be looking at similar triangles, Pythagorean relationship, primary trig ratios, etc. Use the variables whose rates of change are either given or needed. Once you've done that, implicitly differentiate both sides with respect to time, of course doing this before you substitute numbers. Once you've taken the derivative, you can substitute in the values and solve for the variable that you need. Remember, if something is decreasing, the rate must be negative. And then obviously if something is increasing, the rate must be positive. So I have 3 questions that we're going to go through. Let's look at question number 1. So in question number 1, we have a 13-foot ladder, and I say that the ladder is constant, so we're not changing that. So remember, related rates are looking at rates of change, but we're not changing the ladder's length. So it stays 13 feet through the whole question. So a 13-foot ladder is placed against the side of a house. The ladder is not properly secured, and as you climb the ladder slides down the side of the house at a constant rate of 2 feet per second. I want to know how quickly the base of the ladder is sliding horizontally away from the house when the top of the ladder is 5 feet from the ground. Okay, so let's look at this. We have a constant ladder here, and we know that we are sliding down the wall. So this ladder is going down, and as it goes down, the base is going out. So the way that I've labeled my triangle, I just did like with Pythagorean relationship, A, B, and of course the ladder would be C, equaling to 13. So the way that I've drawn this here, the rate of change, dB by dt, it's sliding down, so that's negative, at 2 feet per second. I want to know how fast the base of the ladder is sliding away. And it's sliding away when the top of the ladder is 5 feet from the ground. So in other words, when B is equal to 5. So that's all the information that I'm given. So I need to come up with a formula that's going to relate these sides of the triangle together. And I think the best way to do that would be with the Pythagorean relationship. So Pythagorean theorem says if you square the 2 sides of the triangle forming the 90-degree angle, it will be equal to the hypotenuse squared. So in this case, what we really have is a squared plus b squared is equal to 13 squared, which is 169. And I want to know, do I have enough information? So I want to find dA by dt. So that's the only thing I can't know. And so looking at this formula, I am solving for dA by dt, but I don't know A. So before I get too far into the question, I need to figure out what A is. And I'm looking at a very specific triangle when B is 5. So I want to look at the triangle. Now remember that the ladder is not changing. It will still be 13 feet. Then B is 5, and I want to solve for X. So what I want to talk to you guys about is Pythagorean triplets. So if you're allowed to use a calculator, great, you can do that. And this one's actually not too bad to do by itself, but I want to talk to you about Pythagorean triplets. So any similar triangle that has Pythagorean triplets, here's some example, 3, 4, 5, because 3 squared plus 4 squared equals 5 squared. Or you could have 5, 12, and 13. Now you can multiply all the Pythagorean triplets by the same number to create another Pythagorean triplet. But I can see looking at this Pythagorean triplet when I have a side length of 5 and a hypotenuse of 13, that's one of my Pythagorean triples. So I know that A in this case will be 12 because here's my side B, here was my hypotenuse, and I know side A just by knowing that Pythagorean triplet. So I know that A will be equal to 12. So going back here, I can say that A is equal to 12. Actually, not x, we'll call that a, so we don't get it confused in the question. Okay, so now I only have one unknown, which is dA by dt, so I can take the derivatives of both sides of this equation with respect to time. So the derivative of a squared is 2a with respect to time dA by dt, plus the derivative of b squared is 2b times the derivative with respect to time, and the derivative of a constant is just 0. So now that I've done that, I can just substitute in my values. So 2 times a, which we just found was 12. Now dA by dt is what I'm trying to solve for. And side B had a side length of 5, and dB by dt was -2, and this is all equal to 0. So 2 times 12, 24 dA by dt. And then 2 times 5 times -2 is -20 equal to 0. So to get dA by dt by itself, I will add 20 to both sides. And then I will divide both sides by 24. So dA by dt is going to equal to 20 over 24, which in lowest terms, dividing by 4, is 5 over 6. Now it's going to be positive because it's moving away from the wall. So what I can say is just end this with a statement, something like the base slides away from the house at a rate of 5/6 feet per second. And that would be my answer with the appropriate units. Okay, let's try another one. So we have a plane flying horizontally at a height of 10 kilometers. It flies over a town at noon. If the plane is flying at 500 kilometers an hour, what is the rate at which the diagonal distance between the plane and the town is changing when the plane's horizontal distance from the town is 24 kilometers? Okay, so labeling this triangle here, you can see how I've drawn it. So the plane is flying horizontally, so it's flying like in this direction. And it's at a constant height of 10 kilometers. So that height is constant. It is not changing in this question. So it's flying over a town at noon. The time doesn't really matter. The plane is flying at a rate of 500 kilometers per hour. So the way that I've drawn my triangle, that means that dA by dt, that has a value of 500. So that's the rate of change. Says, what is the rate at which the diagonal distance, that's dC by dt, so I want to know what that is. That's my unknown. What is that rate when the plane's horizontal distance from the town is 24? So in other words, when A is equal to 24. So again, nice relationship between all the sides of a right triangle. I'm going to use Pythagorean theorem. So Pythagorean theorem would say a squared plus b squared equals c squared. In this example, I know b squared, that is held constant. 10 squared is 100 equals to c squared. So if I was to take the derivative with respect to time right now, I have dA by dt, I have a, I have dC by dt, which I'm trying to solve for, but I don't know what c is equal to. So I need to figure out what c is for this particular triangle when a is 24. So not drawing it to scale. The height is always 10. In this particular triangle, we're looking for when a is equal to 24, and we want to find the side length c. So again, you can use a calculator if you're allowed to use one, or we can just go back to Pythagorean triplets. So looking at Pythagorean triplets, I'm looking for which one has side lengths that are in proportion to 24 and 10. If you look at this one here that we used last time, if you times the entire Pythagorean triplet by 2, I would have 10, 24, and 26. And that's exactly what we were given, 10 and 24. So I know that my hypotenuse is 26. So that means that going down here, c is equal to 26, just using my Pythagorean triplets. Okay, so now I can take the derivative of both sides with respect to time. So the derivative of a squared is 2a with respect to time, dA by dt. Derivative of 100 is just 0, equals derivative of c squared is 2c, and then I'll multiply that by dc by dt. So let's plug in what we know. So 2a, 24, dA by dt is 500, equals 2c, so 2 times c, which we just calculated was 26, and then times by dc by dt, which is the quantity that we want. Okay, so on the left-hand side, I'm going to multiply 2, 24, and 500 together, and I will get 24,000, equal to, on the other side, 56 dc by dt. So I'll divide both sides by 52. And then I can leave it as a fraction, or I can put it in as a speed. And because I'm talking about the speed, like the rate of change of that town together, we might want to leave it as a decimal. So if I do 24,000 divided by 52, I'm going to get 461.5, and that will be in units of kilometers per hour. And that would be the rate of change of dc by dt. So what I can say is that the diagonal distance is changing at a rate of that number. So it's changing at a rate of 461.5 kilometers per hour. Okay, let's look at another question, and one in which we're not going to be using Pythagorean theorem. And this will be our last one. So in this example here, we have a spotlight that's on the ground, and it's shining on this wall. So here's the wall. There's, of course, the spotlight. And it's shining on a wall 10 meters away. So the distance of the spotlight to the wall is 10 meters. So we have a man, and he's 2 meters tall, and he's walking away from the spotlight towards the wall, and his speed is 1.2 meters per second. So I want to know how fast his shadow on the wall is changing when he is 2 meters from the wall. Okay, so the way that this diagram is set up is that x is the distance from the spotlight. Let's just define that. X is the distance that the man is from the spotlight. Now, the man is 2 meters tall, so I'll just draw a straight line, or we'll pretend that that's a straight line, okay? And then since x is the distance from the spotlight and the total distance is 10, 10 minus x would be the distance from the wall. So as the man's walking closer to the wall, his shadow is going to get smaller, the shadow being in front of him. So what we have right now, let's see, labeling this out here. So I have x, I have 2, I have the height of the shadow onto the wall is dy, or the y there, and the total distance is 10. So reading this question again, it says that a man is walking from the spotlight towards the wall at a rate of 1.2 meters per second. So that's the rate that you're changing x. So I know that dx by dt is going to equal to 1.2. Or I could write that as a fraction, which is 12 over 10 in lowest terms is 6 over 5. Now I want to know that rate of change when he's 2 meters from the wall. So when this distance here is 2 meters, if he's 2 meters from the wall, he's 8 meters from the spotlight. So this is when x is equal to 8. So let me say that again. When he's 2 meters away from the wall, since the total distance is 10 meters, he's 8 meters away from the spotlight. Now I want to know the rate at which the shadow on the wall is changing. So I want to know dy by dt, but I also don't know y. So I know dx by dt, I know x, I want dy by dt, but I don't know y. So we have to use some similar triangles like we did on the first part of related rates to come up with an expression. So using similar triangles, looking at my big triangle, I know that y is to 10, so y is to 10 as 2 is to x. So as 2 is to x, those are similar triangles because the sides are in proportion and all the angles are equal. So let's multiply both sides of our equation to get rid of the denominator by 10x. So I'm going to multiply both sides of the equation by 10x. So the 10's cancel, I'm left with xy equals the x's cancel 20. So I want a new expression for y. So I can say that y is equal to 20 divided by x. So now that I have that equation, I can now take the derivative with respect to time because I have dy by dt, I have dx by dt, and I also have x. So by taking the derivative with respect to time, since y is just y, the derivative is 1, so I don't even need to know what the y value is. So the derivative of both sides with respect to time. So before I actually do that, when I have 20 over x, I think it would be a little bit easier if we wrote this as 20 times x to the negative 1. So I don't want to use the quotient rule here. So 20x to the negative 1. I think that would be a little bit easier. So derivative of both sides with respect to time. So dy by dt equals 20, take the constant out, times by negative 1 x to the negative 2, and then I'll multiply that by dx by dt. So dy by dt is what we want. So it's all nicely set up for that. So dy by dt equals 20, not negative 20, 20 times negative 1 times x, which is, if I go back here, I've already forgotten. Let's go back up here. What x is 8. There we are. 8 to the negative 2, and then multiplied by dx by dt, which was that 1.2, and I changed that to a fraction, which is 6 over 5. Okay, let's tidy this mess up. So dy by dt equals, so I have 20 times negative 1, that's just negative 20, and then I'm going to multiply that by 6. 8 squared, which is 64, or I can just write it as 8 times 8, comes down here with the 5. Okay, so I'm doing it this way here just in case you don't have a calculator. If you do have a calculator, well, you can just easily figure this out yourselves. So right now what I have is negative 20 divided by 5 is negative 4, and then I can just keep simplifying. So 6 and 8 have a common factor of 2, so I'm left with 3 and 4. Oh, and then my 4's cancel. So dy by dt is going to equal to, in the numerator, I just have a negative and a 3, so negative 3. And in the denominator, I'm just left with 8. So let's state this answer here. So his shadow, so what I can say is the shadow is changing at a rate of, and we were expecting it to be negative because we knew the shadow was getting smaller, negative 3/8 meters per second. And that would be my final answer with the units. So I thought this was a cute little cartoon talking about functions and derivatives since we've been doing so many derivatives. If the function is potato, the derivatives would be French fries. I don't know about you, but now I'm hungry. So I hope that this video helped. You guys can go on and do some practice questions, and I look forward to seeing you for the next one.